guys, back to some pre-algebra here. Still writing some expressions from patterns. So let's get into the second part of this section here. So take a look. So the Pythagoreans also identified and studied the following pattern here. So we have this figure 1 with 1 dot. Figure 2 has 4 dots, right? 2 rows of 2. And then figure 3 is 3 rows of 3. Okay, so the total number of dots, if we want to just get a pattern going here, looks like we have, I want to make a little table. So the figure, and then the number of dots. Okay, figure 1 again had 1. Figure 2 had a total, if we counted those, of 4. Figure 3 is going to have 9. Okay, so what does it appear seems to be going on here? In figure 4, figure 5, figure 6. So figure 4, if we wanted to just draw one more, I guess it looks like it should have 4 rows of 4. Okay, so 4 groups of 4, 4 times 4, right? So 16. Figure 5, then I would expect to have 5 rows of 5, right? 5 times 5. And similarly, 6 times 6. All right, so we kind of answered part A here. Does this pattern, though, have a constant difference, I guess is the question. So do we have a constant difference? So let's take a look. So to get from 1 to 4, we added 3, right? Okay, is that constant? To get from 4 to 9, did we add 3 again? No, we added 5 that time. Okay, to get from 9 to 16, you would have to add 7. To get from 16 to 25, that would be adding 9, right? And 25 to 36 would be adding 11. Sorry, I'm running out of room on the side there. So it's not a constant difference, okay, because it's not adding the same amount. There definitely appears to be a pattern there, right? 3, then 5, then add 7, then add 9, then add 11. So there's definitely a pattern. So what I think they want us to do in part C, describe the pattern in words, though. I would say they want us to describe this pattern, and it looks more like we are just adding, again, it's not a constant amount, but take a look at the numbers, okay? 1, then 4, then 9, then 16, then 25, okay? And if you remember when we talked about exponents, okay, and squaring numbers specifically, the number of dots here is just the figure number squared. Okay, squaring means to multiply by itself, right? Okay, so that should kind of be reasonable from, look at the picture. Figure 2, it's 2 rows of 2, 2 times 2. Figure 3, 3 rows of 3, 3 times 3. That's exactly what it means to square a number, okay, multiplying by itself. So if we wanted to continue down and say, all right, what about if we went all the way down to the 10th figure? Again, the pattern here appears to be 10 times 10, okay, which we know should be 100. Okay, and we determined our answer by just squaring the number. All right, how many pebbles would there be in the 40th figure? Okay, so again, would you want to continue this pattern out and have to draw 40 figures? No, right? We know a pattern. We said that the number in the figure, the number of dots, is going to be that number times itself. Okay, so if I were to do 40 times itself, okay, or 40 to the second power, 40 times 40 is going to be 1600. Okay, and then in the nth figure, let's just say we want a variable. I want to be able to pick any number I want. That's the point of a variable, right? It changes. It's gonna work for any number. So in the nth figure, again, all we're doing is taking n and multiplying it by itself, or we can write that using exponents as n squared. Okay, and the Pythagoreans called this number, the numbers in this pattern, the square numbers. Okay, hopefully it's pretty clear why that is. Okay, the figures were squares, and then of course, again, we can write this as an exponent as squared. Okay, and there's definitely a relationship going on there. All right, so let's take a look. Let's move along. Number 8 here. The numbers in the pebble pattern shown below are called the rectangular numbers. Okay, so not square numbers this time, right? But rectangular numbers. So we see figure 1 has 2 rows with 1 each. Figure 2 has 3 rows with 2 each. Figure 3 has 4 rows with 3 each. Okay, so let's think about how many do we have here. So we had 2 total dots there. We had 2, 4, 6 there. 3, 6, 9, 12 there. Okay, so what would happen in the next figure? Okay, the next couple figures. So let's think about what was going on here. So again, this one, there were 2 rows with 1 each. Okay, in figure 2, there were 3 rows with 2 each. Okay, then we had 4 rows with 3 each. Okay, so in the fourth figure, if this pattern continued, okay, it should be then 5 rows with 4 in each row. Okay, we should have 20 in the fourth figure. Okay, it's 5 times 4. In the fifth figure, it should be 6 times 5. And in the sixth figure, it should be 7 times 6. Okay, or 42. Okay, so really it's just the figure number. You know, it may make more sense to write these instead of writing 2 times 1. We could do like 1 times 2. That would be equal, right? Or 2 times 3. 3 times 4. That way we can maybe see the pattern a little bit better. It's just taking the figure number times the next number up, right? Like for example, again, the fifth is just 5 times 6. The sixth is just 6 times 7. Okay, so that's going to be a pattern that's giving us these rectangles. Okay? And again, rectangles can have any different sort of shape to them as long as they have, you know, like a rectangle, right? It has 4 right angles from the 90-degree corners, but it doesn't always have to be one unit taller than it is wide. They could be different lengths and stuff, but this is just a specific instance of that. But let's take a look. In this pattern here, is there a specific constant difference again? Okay, so our pattern again, our number of dots went from 2 to 6 to 12 to 20. Okay, and we can kind of see, hopefully quickly, to get from 2 to 6, that increased by 4. Okay, but to get from 6 to 12 did not increase by 4 again. So definitely not a common difference. This is definitely changing at a different rate. Okay, let's see, can we figure out now how many figures would there be in the 10th figure, or how many dots I should say. So to get in the 10th figure, again, the pattern is you're just taking the figure number times the next number up. So 10 times 11 should be 110. Okay. How many in the 30th figure? Again, same thing. In the 30th figure, we're just going to take 30 times the next number up. 30 times 31. Okay, I'm just going to verify. I believe it's 930, and it is. Okay, so for the nth figure, again, for a variable, in the nth figure, it's just going to be n times the next number up. Now, what's the next number up past n? N plus 1. Right? We don't know what n is, but the next number would always be it plus 1. Okay? All right, number 9, and one more little pattern I think they're going to show us in here. The Pythagoreans called the numbers represented by the pebbles in this pebble pattern the triangular numbers. Okay, so why do you think this is triangular? Right, look at the shape. Okay, we started out in the very first example with square numbers. Then we got to these rectangular patterns here in number 8 there. And now we have these triangular numbers, so they're forming a triangle when we're forming the figures in a diagram. All right, so let's take a look at how many pebbles there are in here. So figure 1, we can see clearly has 1 dot. Okay, figure 2 has 3 dots. Figure 3, 1, 2, 3, 4, 5, 6 dots. Okay, and let's make a quick comparison to what was happening with the rectangular pattern above. If we compare these numbers, okay, and also kind of look at the shape, to go from 1 to 3 to 6, how that compares to what we had up here, it was 2, then 6, then 12. Okay, if you look at the numbers down here, number 9, in this triangular pattern, they're half of what they were before. Okay, and if you think about that, that's because the figure is taking half of what it was above. Take a look specifically at, for example, figure 2. Figure 2 had those 6 dots. Down here, let me actually draw figure 2 a little larger down here. Figure 2 above was this. Okay, this was figure 2 from the rectangular numbers. To make it the triangular figure 2, notice how they just kind of took half of the rectangle, right? We took the bottom right corner of it in a way, which would be basically like taking these 3 numbers from the figure above. So it's taking half of it, just like down here, taking those is taking half of the figure 3 above. Okay, so the triangular is like the bottom half, the bottom right half of a rectangle, right? If you kind of can visualize that, you know, here's a rectangle again, and to make it the triangular numbers, we're taking kind of that half of it. Okay, we do that one. Was it down here at the? We wrote a pattern somewhere, didn't we? Yeah, here it is. When we wrote this pattern right here, n times n plus 1, right, that gave us the number of pebbles for the rectangular pattern, right? So if we want to show half of that, okay, one way to show half of something is to divide it by 2. So if we want to look into this pattern, you know, how is the triangular number pebble pattern related to the pebble pattern of the rectangular numbers? It's going to be half the amount. Okay, and again, visually, you can hopefully see, you know, a rectangle, let me draw one more, is really just comprised of 2 triangles like that. You have one down here, and then you have a second one, you know, up here. And that's kind of why if when you get into geometry, if you've done any area of triangles, the area of a triangle is going to be 1/2 the base times the height, while the area of the whole rectangle doesn't have that half there. It's just base times height. Okay, and that's kind of why that goes together. So let's see if we can use this. Can we use our response to part B to write an algebraic expression for the number of pebbles in the nth triangular term? So let's recall again the rectangular expression that we wrote was, again, going back, we should be able to take this, again, let me just rewrite, this was the rectangular one, n times n plus 1. So the triangular, I'm just going to use a triangle as an abbreviation, would need to be n times n plus 1, but again, take half of that, divide it by 2. Okay, let's dig into that a little bit. That one's a little complicated. Let's verify by substituting n equals 4. Okay, so if n equaled 4, and we wanted to plug it into that rule, n would be 4, so it would be 4 times, I'm just going to show the whole thing, 4 plus 1 over 2, okay, which is really 4 times 5 over 2, okay, which is really just 20 over 2, which is really just, a lot of really just here, is really just 10. Okay, is this result the number of pebbles in the 4th triangular number? It is, okay, it sure is. Can we use our expression now to predict, okay, if we had the triangular pattern going, all right, how many pebbles would there be in the 30th triangular number? Okay, so we have ourselves a formula to use, or an expression, right, for triangular numbers. And we're going to use 30 for n. So it's going to be 30 times n plus 1. So 30 plus 1 is 31 over 2. Okay, and if we just simplify that, 30 times 31 is 930. If we divide that by 2, we're going to get 465. Okay, so using these expressions can help us, evaluate our pattern at farther out along in the pattern without really needing to know every single term in the pattern. Okay, we could have drawn all 30 figures. Okay, probably wouldn't be fun. Definitely wouldn't be fun. But it would have got the job done. But knowing and understanding the expressions make that much easier. Okay, so let's do a brief little summary of the patterns we saw today. The square numbers. Okay, and that was the pattern was just take n and square it. So the first ones were just, of course, 1. Then 2 squared was 4. 3 squared is 9. 4 squared is 16, etc. Okay, we saw that one first. Then we went to these rectangular numbers. Okay, where it was a rectangle where the height and the length and height were one number apart. So we ended up using the formula of n times n plus 1 to get the number of dots. And then the last one we just saw was the triangular numbers, okay, which we ended up showing the pattern there was, it was basically just half of the rectangles, right? So we can take the n times n plus 1 and divide it by 2, okay? And that's where we're going to get our pattern there from that. Okay, so those are the three. Again, these do not have a constant difference. Okay, so they're a little different than what we saw at the beginning, but there's still a pattern there, and we were still kind of able to come up with an expression to evaluate the pattern. All right.